We are going to be determining if the following sequence or series converges. Now, a sequence converges when you find the limit as n approaches infinity and we get some finite value. All right, so let's check out this one. Determine if the sequence ln n over n squared converges. To determine if this converges, I'm going to be using L'Hopital's rule. I'm going to be using L'Hopital rule for this one. Using L'Hopital rule, it tells us that we can find the limit of this as n approaches infinity by finding the derivatives of each. So using L'Hopital, we can say the limit as L approaches infinity of ln n over n squared. We can use L'Hopital's rule and say that is going to be equal to the limit as n approaches infinity of, what we're going to do now is we differentiate ln n. Differentiating ln, we get 1 over n divided by, when you differentiate n squared, you get 2n. Now you have 1 over n over 2n. Applying n equal infinity, 1 over infinity is 0. So get 0 over infinity, because when you put in infinity here, now it's infinity. 0 over infinity is 0. This is 0. And so yes, this sequence converges. So this one converges. Easy. All right, now let's look at the next question right here. The next question says, find the nth term of each sequence and use it to determine whether or not the following sequence converges. So let's find the nth term. Finding the nth term of this sequence right here, as we can see, this is really 2 over 1. So in the numerator 2, 3, 4, 5, 6. So in the numerator, the nth term is just n plus 1 over 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So the nth term is n squared. What we're going to be doing is we're going to be evaluating the limit as n approaches infinity of n plus 1 over n squared. We're finding the limit of n plus 1 over n squared. Now the limit of n plus 1 over n squared, that is just going to be equal to, there are many ways we could do this. We could divide through by the highest power of n. Dividing through by the highest power of n, what you get is the limit as n approach infinity of, so we divide through by n squared. N over n squared is 1 over n plus, right here now we have 1 over n squared, 1 over n squared over, divide n squared by n squared, you get 1. Then all we need to do is plug in infinity now. 1 over infinity is 0 plus 0, so we get 0 over 1. Since we get 0 over 1, which is 0, then we know that this converges to 0. So the second example also converges. All right, nice. Now let's look at part B right here. Part B gave us 1, which is really 1 over 1, 1 over 2, 1 over 6, 1 over 24, 1 over 100. So the next one is 100 over 720, and it going on. So the nth term is 1 over n factorial. This is 1 over n factorial. So since we have 1 over n factorial, we need to determine if this is converging or diverging. All right, but clearly this we know that this is converging, but just to show the working, we need to show that the limit, find out the limit as n approaches infinity of 1 over n factorial. Find the limit of 1 over n factorial. All right, now there's an easier way to do this one. All right, there's an easier way to do this, because this right here, all you need to do is just plug in infinity, and we know that infinity factorial is super huge. 1 over a huge number is just 0. So clearly this is converging. As we can see, definitely looking at this, it was straight away converging. So the first 3 so far, really easy. These are all converging. This converges. All right. Now here, these look a little more better to do. Use the nth term test to determine whether or not the following series converge. Now listen what it said to use. Use the nth term divergence test. The divergence test tells us that we just need to show that as long as this term does not go to 0, as long as the nth term don't go to 0, then it diverges. So what we're going to be doing for part A, we're evaluating the limit as n goes to infinity of the nth term. What is the nth term? The nth term is 1 plus 3n squared plus n cubed. 1 plus 3n squared plus n cubed over 4n cubed minus 5n plus 2. This is what we have. Now to evaluate this limit now, we're going to divide through by the highest power. We're going to divide through by the highest power of n. Dividing through by the highest power of n, what we're going to get is the limit. We're going to get the limit as n approaches infinity of, dividing through by the highest power of n. The highest power of n is n cubed. So we get 1 over n cubed plus 3n squared over n cubed is just 3 over n plus, now n cubed over n cubed, n cubed over n cubed is 1 divided by 4n cubed over 4n cubed is 4 minus 5n over n cubed is 5 over n squared plus 2 over n cubed is just 2 over n cubed. Good. Now when you apply n equal infinity now, 1 over infinity is 0. 3 over infinity is 0 plus 1. So we get 1 in the numerator over, apply n as infinity now, 4 minus 5 over infinity is 0 plus 2 over infinity is 0. So it works out to be 1 over 4. But 1 over 4 is not 0. So that means that the last term don't go to 0. When you're doing summation, it's a little bit different from a sequence. If this was a sequence, we would have said that the sequence converged to 1 over 4. But for series, whenever the last term is not going to 0, it diverges. So this one diverges. That one diverges. All right, so we might need a little more space. So let's do the next one on the white screen. the sum from 1 to infinity of 1 over n squared. So we want to work out the sum from 1 over n squared, and we want to evaluate the sum from n equal 1 to infinity. Now again, we're just going to use a divergence test, and the divergence test tells us to work out the limit as n approaches infinity of the nth term. So we're working out the limit as n approaches infinity of 1 over n squared. Plugging in infinity, what we get is 1 over infinity, which is 0. Since we get 1 over 0, then this clearly converges. This converges. So good. This converges. So nice. So we can say this converges. So this one converges because the nth term is going to 0. So this one converges. Now let's look at part C. Part C says to evaluate the sum from n equal 1 to infinity of n factorial over 2n factorial plus 1. To do that, all we need to do is find the limit of the nth term because we're using divergence test. So let's do that. So we're supposed to determine if this converge or diverge. N equal 1 to infinity of n factorial divided by 2n factorial plus 1. Now all you have to do now is, for this right here, we're going to just be evaluating the limit as n approaches infinity of n factorial over 2n factorial plus 1. So then you might say, so sir, what is the method to do? Well, all you have to do now is you're going to divide through by the highest power of n. The highest power of n is n factorial. So dividing the numerator and the denominator by the highest power of n, we are going to get the limit as n approaches infinity of n factorial over n factorial, which is now just 1, divided by 2n factorial. So maybe I need to show that step. I keep saying dividing the highest power of n, but you don't know where it comes from. So we're dividing by the highest power of n, which is n factorial. We're dividing every term then by n factorial. So we can see that step now. Divide every term by n factorial, 1 over n factorial. Doing that now, what we get is n factorial over n factorial is 1. So we end up with the limit as n approaches infinity of n factorial over n factorial, which is 1 over 2n factorial over n factorial is 2 plus 1 over n factorial is 1 over n factorial. Plugging in n as infinity, we get 1 over 2 plus 1 over n factorial is 0, so we get 1 over 2. But 1 over 2 is not equal to 0, and so this diverges. This diverges. So this one right here diverges. Part C diverges. This diverge. Now let's look at the final one now. The sum from 1 to infinity of n plus 2 factorial over 10x factorial. So we're working out the sum from n equal 1 to infinity of n plus 2 factorial, n plus 2 factorial, that is being divided by n, 10n factorial, 10n factorial. Now, first things first, what we need to realize is that this right here, you can rewrite this summation, but let's say you didn't even want to rewrite it. So all we're finding is the limit as n approaches infinity of n plus 2 factorial over 10n factorial. N plus 2 factorial divided by 10 multiplied by n factorial. All right. So now what this works out to be is, what we can realize is that this n plus 2 factorial right here, we can rewrite it as, I left off the limit sign, my apologies. So write back the limit as n approaches infinity of, now that n plus 2 factorial right there, rewrite that as n plus 2 times n plus 1. This is now n plus 2 times n plus 1 times n factorial. Yeah man, this is it. N plus 2 times n plus 1 times n factorial being divided by 10 times n factorial. Then guess what happened? This n factorial now cancels this n factorial right here. So now we're just ending up evaluating the limit as n approaches infinity. Now we're evaluating the limit as n approaches infinity of expanding this now, which is just n squared plus 3n plus 1. Is that 3n, 2n, and n? Yeah, 3n plus 1 over 10. That's what we're evaluating now. Then now, you can divide through by highest power of n. We're going to divide through by the highest power of n, because clearly we see that this diverges, but just to say you want to simplify it as far as possible, we're now just evaluating the limit as n approach infinity of n squared over n squared is 1 plus 3n over n squared is 3 over n. 1 over n squared is 1 over n squared. And then 10, then this is now 10 over n squared. 10 over n squared. So we apply in n as infinity now, the numerator we get 1 plus 0 plus 0. So we get 1 over, plug in infinity now, 10 over infinity is infinity. 10 over infinity. 10 over infinity is 0. And 1 over 0 is infinity. And so this one clearly diverges. That one diverges. So this one diverges. This one diverges. Now also, what I want you to do is, as you're working out these questions, I am going to introduce you to Symbolab. Symbolab is a nice way to also check to show that whatever you're doing diverges. As you can see here, this was the third example. You plug it in, diverges. All right. So this one we just did was, I think it was n plus 2 factorial. N plus 2 factorial divided by 10n factorial. You're going to see it should diverge. Let's see. There you go, diverges. So whenever you do a question, you can put it in Symbolab to check your solution. So it is just www.symbolab.com. www.symbolab.com. I'll leave a link in the description. All right. So continuing now, question 4, it says, what is the sum? What is the sum of the sum from 1 to infinity of 1 over n plus 1 minus 1 over n plus 3? Now, all we're going to do is use partial sum to do this. As we can see right here, what we're going to do is do the sum for this part first. So when n is 1, we know that we would get 1 over 2 plus when n is 2, we would get 1 over 3 plus we keep on applying, keep on adding and adding and adding and adding. All right, keep on adding and adding and adding. What I'm going to do for now, before I evaluate the sum from 1 to infinity, I'm going to add up to the rth term. Up to the rth term, I would say I would add up to plus 1 over r plus 1. You might say, why am I stopping right here? Just look what I'm doing to evaluate that. I'm going to stop it right there. Minus, if I were to plug in now from n equal 1 on this side, I would get 1 over 4 plus 1 over 5 plus, I continue, then I plug in all the way up to when I have r equal r minus 1, I would get 1 plus 1 over, this would be r plus 2, and then the last term would be plus 1 over r plus 3. This would be the last term, 1 over r plus 3. That would be the last term. Now, why would I do that? Because look at this. The 1 over 4 would cancel the 1 over 4 here. 1 over 5 would cancel the 1 over 5. The 1 over r plus 1 would cancel the 1 over r plus 1 in here. And so what I would be left back with is 1 over 2 plus 1 over 3. We'll be left back with 1 over 2 plus 1 over 3. Left back with 1 over 2 plus 1 over 3 minus, this would be minus now, 1 over r plus 2 minus 1 over r plus 3. Now what I'm going to do to evaluate that summation now I'm going to plug in infinity. Now I can plug in infinity because 1 over infinity is 0, 1 over infinity is 0. So that means that this sum would actually be just 1 over 2 plus 1 over 3. So this final answer works out to be 1 over 2 plus 1 over 3. I can't know that. 1 over 2 plus 1 over 3, which is 5 over 6. So this works out to be 5 over 6. So first what I did was found the sum from 1 to the rth term or the kth term, whichever letter you want to use, then plug in infinity, because when you plug in infinity, this becomes 0, this becomes 0. So you just get 1 over 2 plus 1 over 3 minus 0 minus 0. You just get minus 0 minus 0. So now, for those who are not so inclined to believe it, let us go ahead and evaluate the summation using Symbolab. So here in Symbolab, just to evaluate it, the sum from 1 to infinity of, I think this was 1 over n plus 1 minus 1 over n plus 3. Evaluate this. There it is, 5 over 6, just like what we get, 5 over 6. All right? Yes, converges to 5 over 6, and we said that is what the sum is. All right? So that's 5 over 6 for true. Now this says, using your calculator to verify that the sum of the partial fraction is bounded, it wants us to evaluate S500. Now, S500 just means it wants to find the sum from 1 to 500. So now what it wants us to do is find the sum from 1 to 500. Now the sum from 1 to 500, and what it's going to show us is, since it's bounded, it's saying that the sum won't be bigger than this. The sum will not be bigger than this, but it will be close to this. That's what it wants us to verify. Pretty much want to show to verify that this right here, converges and that the sum is 5/6. So let us verify that. So now we're going to evaluate the sum from 1 to 500 of 1 over n plus 1 minus 1 over n plus 3. All right, so evaluating this sum, evaluating this right here, this is just going to be equal to, when you put in the first part, when you put in the from 1 to 500 for this side, we know we're going to get 1 over 2 plus 1 over 3 plus all the way up to 500 becomes, putting in as 500, the last one going to be 1 over 501. Good. Now close up that. Then what we're going to do now is plug in from 1 to 500 on this side. This one going to start from 1 over 4. Then we're going to go 1 over 5 plus all the way up to, now look at this. If you plug in the 498 term, the 498 term would be 498 plus 3, which is 1 over 501. Then if you put in the 499 term, you get plus 1 over 502. Then if you put in now the last term, you get 1 over 503. And you might say, why I show you that? Why do I show you all of that? I show you all of that simply because the 1 over 4 cancels the 1 over 4 here. 1 over 5 cancels the 1 over 5 here. 1 over 501 cancels the 1 over 501 here. And so what we're left back with is the 1 over 2 plus the 1 over 3. And then doing the subtraction, now you get minus. This is now minus the, this is now minus 1 over 502. This is now minus 1 over 502 minus 1 over 503. That's what we get. All right. So now when we get that, now what we get is this. You just put all of this in a calculator and that will give you the sum from 1 to 500. So putting that in my calculator, I get 1 over 2 plus 1 over 3, 1 over 3 minus 1 over 502 minus 1 over 503. I get 0.829. Oh, this should be 3. So I get 0.829. That's what I get for my final answer. Now, of course, for verification, let's check it. Let us check it. The sum from 1 to, not infinity, but 500 should get 0.829 as well. Now this says use the indicated test for convergence to determine if the series converges or diverges. If possible, state the value to which it converges. All right, use the indicated test for convergence to determine if the series converges or diverges. If possible, state the value to which it converges. And it wants us to use the convergence test. You have to use what they tell you. All right, in CAPE, they won't tell you what to use, but this one says using the convergence test. Now, what is the convergence test? The convergence test tells us that if the sum converges, then the limit must approaches 0. All right. If the sum converges, then the limit must approaches 0. So let's write it in summation form. This is really 3 over 1. So rewriting this geometric series here, this can be rewritten as the sum from the numerator. We got 3, 15, 75. So we're multiplying by by 5. So it's going to be In the numerator, it's a times r to the n minus 1. A is 3. So it's 3 times 5. It's 3 times 5 to the r minus 1. Since we're using n, then it's going to be n minus 1. This is now 3 times 5 to the n minus 1 over, in the denominator is what? 1, 4, 60, multiply by 4, multiply by 4, multiply by 4. And the first term is 1, so this is just 1 times 4 to the n minus 1. That's how you rewrite this in summation form. So now what this is actually is just to write it better, this is just the sum. This is just a sum from 1 to infinity of, this can be put as 3 times, in bracket, 5 over 4, 3 in bracket 5 over 4 to the n minus 1. All right. Now what does the convergence test tell us? The convergence test tells us that if the summation converges, which it is, then the limit of the nth term must go to 0. So all we need to do is show that the limit of the nth term is going to 0. So let us see. So the limit of the nth term, the limit as n approaches infinity, right, is going to be, this limit of this nth term is 3, the limit of 3 times 5 over 4 to the n minus 1. All right. Now look at this. As n approaches infinity, is this going to converge? Now, of course, the best way I would do this is by D'Alembert's ratio test. I'm going to do this using D'Alembert's ratio test. It's just the easiest one for me, so let's do it right here using D'Alembert's ratio test. So the limit as n approaches infinity of 3 times, this was 3 times what? I think it was 5 to the n minus 1 over 3 times 5 to the n minus 1 over 4 to the n minus 1. All right. All right. Now, many persons might say, looking at this now, both of them to the 5 to the n minus 1, you might want to be inclined to divide through by 5 to the n minus 1, but would that be helpful? If you divide through by 5 to the n minus 1, what you would get is, yeah, let's do it that way and see. We're going to divide through by the highest power, which is 5 to the n minus 1, and we're going to get the limit as n approaches infinity of, this becomes, limit of the product is the product of the limit. This becomes a limit of 3 times the limit as n approaches infinity of, we're going to divide through by the highest power of n now for this part. So we're going to have 5 to the n minus 1 over 5 to the n minus 1 over 4 to the n minus 1 over 5 to the n minus 1, which is just 4 over 5 to the n minus 1. So we divide both the numerator, denominator by the highest power. All right, now this works out to be the limit as n approaches infinity of 3 is just 3. Then we get times, this becomes now the limit as n approaches infinity of, so we plug this in now, plug it in. 5 to the n over 5 to the n is 1, so it's 1 over 4 over 5 to the n minus 1. 1 over 4 over 5 to the n minus 1. Now, if we plug n as infinity in here, a fraction to some big number goes to 0. A fraction to some big number goes to 0, and 1 over 0 is infinity, and infinity times 3 is infinity. This is going to infinity. Since this is going to infinity, it does not converges. So this does not converge. So this one here does not converge. This does not converge. This diverges. So this one diverges. Of course, we could have used D'Alembert's ratio test to show it. So this one diverges. All right, now of course you always want to see some verification. So I will give you verification. From 1 to infinity of this was 3 times, when the numerator was 3 times in bracket 5 over 4. Now all of this was raised to the n minus 1. So there you go. You're going to get diverges. There it is, diverges. So it indeed diverges. All right. And if you just want to check that you created the correct formula as well, if you were to evaluate the sum from 1 to 5, you're going to get back the same 5 terms that you saw in there. You're going to get back your same form right here. You're going to get back the same. All right. I wanted to just show you that if you plug in from 1 to 1, you get back your first term. Just for verification, you get back your first term, which was 3. Plug in the sum from 1 to 2, you get the 3 plus the second term, which was 15 over something. All right, the second term, when you plug in 2, you get 27 over 4, and look at this. The first term was 3. When you add 3 and 15 over 4, you get the 27 over 4. So I'm just showing you that the formula that we create is correct. 3 is 12 over 4. 12 plus 15 is 27, 27 over 4. So I'm just showing you that indeed the formula is correct. So as the formula showed you, it diverges. Just to go back twice, we can see it diverges. There it was right here. It diverges. Just want to show again. So what we did was absolutely fine. I didn't bother to use D'Alembert's ratio test. Sometimes it's just depending on, just how you feel in the moment. Now this one is another geometric series, and I want to show that this diverges now or converges. Now, as you can see, the first term is a half, a quarter, 1 over 8. So the common ratio of this geometric series is the second term divided by the first term. The common ratio is 1 over 4 divided by 1 over 2. Now, once you get a geometric series, 1 over 4 divided by 1 over 2 is a half. Now, remember what we said about geometric series. Once the common ratio is between 1 and minus 1, it converges. A half is between 1 and minus 1. So this one straight away converges. This one converges. Without doing anything, we know that converges. So this converges. Easy, soft. Now this question, part C, this says evaluate, determine if it converges using the P-series method. The P-series method is the power series method, and all it states is that anytime the power is less than 2, it diverges. Anytime the power is greater than 2 in the power, it converges. So you'd have to rewrite this as the sum from n equal 1 to infinity. This is the sum from n equal 1 to infinity of n to the minus 2 is 1 over n to the 2/3. That's what we have. But look at this. 2 over 3 is less than 2. So since 2 over 3 is less than 2, then this one diverges by P-series method. By P-series method, this one diverges. That's known as the P-series method. If you don't want to use the P-series method, you can go ahead and use D'Alembert's ratio test. All right, so this one diverges. All right, for verification, check it out in Symbolab. Now the integral test for this now. We want the integral test for the sum from 1 to infinity of 3n over 2n squared plus 3. So the integral test from n equal 1 to infinity of 3n over 2n squared plus 3. Now what you're going to get is, you plug in, it says use the integral test, so we're going to do a little bit of integration. We're integrating from 1 to infinity of 3n over 2n squared plus 3. Now, the differential of the denominator is not in the numerator. So what we're going to have to do is the differential of 2n squared is 4n. So we need a 4n in the numerator. So in order to get a 4n, what I'm going to do is multiply it by 4 and then put a 1 over 4 out here. Then when I put a 1 over 4 out here, I'm going to factor out this 3 right here and put the 4 in front of the n right there. So I'm going to put the 4n right here and put the 3 right here. Then you might say, sir, that's crazy. No, it's not. Look at this. I didn't change the value. 3 over 4 times 4 is 3. 3 over 4 times 4 is 3. 3 over 4 times 4 is 3. So what does that mean? That means that I didn't do anything wrong. All right? 3 over 4 times 4n is 3. So that means this 4 right here, multiplied by this 3 over 4, give me back 3. Not going to say it any more time. And we're going to integrate this now with respect to n. So now we can go ahead and integrate this. Whenever the differential of the denominator is in the numerator, it's ln the denominator. So we get 3 over 4 ln. You get 3 over 4 ln the denominator, where the denominator is 2n squared plus 3. And we're integrating, of course, we're integrating from 1 to infinity. Integrating from 1 to infinity. Now, as you can see here, ln of infinity is just a big number. Ln of infinity is a big number. Plugging in infinity, what are we going to get? Plugging in infinity, you're just going to get infinity. Plugging in 1, you're going to get ln. Just plugging in infinity, you're going to get infinity. This is going to be working out to be 3/4 times. Ln of infinity is a big number. That's just infinity minus, plug in 1, that's just ln 5. But this is still just infinity. So this diverges. This diverges because this is not going to a finite value. So this diverges. So this one diverges. Nice. All right, so of course, I'm going to show you it in Symbolab now. So let me plug it in. So putting it in Symbolab, here it is. The sum from 1 to infinity of 3n over 2n squared plus 3 diverges. Did I put it in right? Is that 3? Yep, so 3n over 2n squared plus 3, clearly it diverges. All right, so that's how you do it using the integral test. All right, part E. Part E is to use direct comparison to evaluate the sum from 1 to infinity of e to the n over n. So if you're using direct comparison to evaluate this, direct comparison means D'Alembert's ratio test. Direct comparison means D'Alembert's ratio test. That's direct comparison. So to use direct comparison to evaluate this, all we're going to do is find the limit. We're just going to find the limit as n approaches infinity of. Now, remember D'Alembert's ratio test, it is un plus 1 over un. So it's going to be un plus 1 is e to the n plus 1 over, replace n with n plus 1. So it's e to the n plus 1, n plus 1, because this is your un. This is therefore your un plus 1. Then it is divided by your un. Your un is just e to the n over n. So what we're going to get is this works out now to be, when you're doing division, you can reciprocate. You can reciprocate. That will become the limit as n approaches infinity of, this now becomes e to the n plus 1 over n plus 1. And then you reciprocate and change the sign to multiplication. This becomes multiplying by n over e to the n. Now look at this now. This part now, e to the n plus 1 times n over e to the n, that will just become the limit as n approaches infinity of. This is now the limit as n approaches infinity of. Now the e to the n plus 1 over e to the n is just e to the 1. So you get e to the 1 times n over n plus 1. That's what we get. Yeah, man. Yes. Now, since this is what we get, then this just becomes, we can break the limit as the product of their limit. So that's now just the limit as n approaches infinity of e to the 1. Limit is as n approach infinity of e to the 1 multiplied by, we can break this up as multiplied by, divide through by the highest power of n in here. That becomes 1 over 1 plus 1 over n. Yeah, man. But then look at this, plugging in n as infinity. Plugging in n as infinity, 1 plus infinity is 0. So we get 1 over 1. So when you plug in infinity now, you get e times 1, which is e, but always remember e is 2.71, which is greater than 1. And so this diverges. By D'Alembert's ratio test or by direct comparison, this one diverges. Diverges. Let's look at direct comparison now. Using direct comparison, I'm going to do this one on the whites. Using direct comparison for the sum from 1 to infinity of 3 to the n over 7 to the n plus 1. So the sum from 1 to infinity of 3 to the n over 7 to the n plus 1. Now, all we're going to do is the plus 1 in the power. Nope, it's not in the power. So this is your un. That is your un. That's your un. Your un is 3 to the n over 7 to the n plus 1. That's your un. Now, what is your un plus 1? Your un plus 1 mean you replace n with n plus 1 to get 3 to the n plus 1 divided by, this is now 7 to the n plus 1 plus 1. That's what you get. So since this is what we get, continuing, what we're going to get now, therefore, is un plus 1 divided by un. That's going to be equal to 3 to the n plus 1, 3 to the n plus 1 divided by 7 to the n plus 1, 7 to the n plus 1 plus 1, and it is being divided by un. This is un. When you're dividing, this is un. When you're dividing, instead of writing out this divide, I'm just gonna write multiplied by, and I reciprocating it. 7 to the n plus 1, 7 to the n plus 1 over 3 to the n. Yeah, man, that's what we have. So now I can evaluate this now. To evaluate this, I'm going to bring the 3n over here. I'm going to write it as 3 to the n plus 1. Write it as 3 to the n plus 1 over 3 to the n multiplied by 7 to the n plus 1 over, this is now 7 to the n plus 1 plus 1. Now, as we can clearly see, 3 to the n plus 1 over 3 to the n, that is just 3. So we get 3 times, this is now 3 times in bracket, 3 times in bracket, 7 to the n plus 1 over 7 to the n plus 1, 7 to the n plus 1 plus 1. Now you might say, blues and skirt, what are we to do now? Well, don't worry. We're just going to evaluate the limit of this now as n approaches infinity. So now the limit as n approaches infinity, the limit as n approaches infinity of un plus 1 over un, this is now just going to be equal to the limit, this is now just the limit as n approaches infinity of, this is now the limit as n approaches infinity of, this is now 3 times, let's look back what it was, 3 times 7 to the n plus 1, 3 times 7 to the n plus 1 divided by 7 to the n plus 1 plus 1. Now in this bracket right here, we're going to divide through by the highest power of n. In this bracket, divide through by the highest power of n. Dividing through by the highest power of n, what we're going to get is the limit as n approaches infinity of, this is going to become 3 times, now 7 to the n, it's going to become 7 to the n over 7 to the n plus 1 over 7 to the n over 7, we're dividing through by the highest power, this is n plus 1, n plus 1. Now 7 to the n plus 1 over 7 to the n plus 1 is 1 plus 1 over 7 to the n plus 1. Now we can evaluate the limit, because now when we put in n as, when we plug in n as infinity, we can evaluate this limit, because 7 to the n over 7 to the n plus 1, when the bases are the same, we subtract the powers, and so this becomes 1 over 7. So we can even rewrite this part now as just 1 over 7. That part is 1 over 7. So if plugging in n as infinity now, this part right here, infinity, this is what? 1 over infinity, 0. 1 over infinity, 0. So plugging in that now, infinity, we get 3 times 1 over 7. So we get 3 times 1 over 7 plus 1 over 1 plus 0. So it works out to be 3 times 1 over 7, which is 3 over 7. By D'Alembert's ratio test, since 3 over 7 is less than 1, it converges. So this one converges. So example 2 converges. So this one right here converges. So this converges. Of course, anything I do, I like to verify. So I'm going to verify with you with symbol of that it indeed converges. So it was the sum from 1 to infinity of 3 to the n over 7 to the n plus 1. 7 raised to the n plus 1. Just to verify to you that it converges, we shall see. There it is, converges. Wonder what method they use. They apply series ratio test. We didn't do series ratio test. We did the direct comparison or the D'Alembert's ratio test. That's what we use. We didn't use series ratio test. All right, so we know that it converges. Now, this one now is the easiest one, limit